Hello, and glad to see you with this first topical session on the safeND. And our session is on various aspects to storage, conditioning, and transport. My name is Christoph Bunzmann. I'm head of licensing affairs in BASE, and I'm honored to chair that session together with.
My name is Florence Sontuc. I'm head of department for decommissioning and storage at GRS in Cologne, and I'm very glad to co-chair this session with Christoph Bunzmann. And I would hand over the microphone back to Christoph to announce our first speaker for today. As long as we're waiting for our second speaker, we hope that he will arrive soon. So, please.
Thank you, Florence. So, we've got technical issues. So, let's see. I really should have printed that, but it will work. So, our first speaker is so now it's working. Okay, so we hope our second speaker will be here soon. So, our first speaker is Sarah Weick, and she has a bachelor and master in geosciences at the University of Göttingen, and she's now a PhD at the Karlsruhe Institute of Technology on the Spitzwurz project. She might talk about that later. She's working at the High Temperature Materials Chemistry Group of Martin Steinbrück at the Institute of Applied Materials and Applied Materials Physics. So, Sarah, the floor is yours.
So, that's okay. I can use it. So my talk will be about experimental investigations with neutron radiography of hydrogen effects by elastic stresses on cladding tubes under conditions similar to interim dry storage. Of course, this project was named already, Spitzwurz. This is connected to this kind of experimental research. So I give you a short introduction about spent nuclear fuel in general and hydrogen in zirconium that you probably are already familiar with. And I show you some setup and methods that we use, some analysis methods, and then some results in conclusion. So generally, to give you a short introduction about spent nuclear fuel or the lifetime, you might be familiar already that we have the reactor operational phase, and then a wet storage phase, vacuum drying phase, and the vacuum drying phase ends with a temperature rise of about 400 degrees. So these 400 degrees are basically the starting temperature of the interim dry storage phase that is relevant for the project. The period is also characterized by a very slow cooling process, and during this process that lasts for decades, also we don't have a final repository yet, we kind of reach very low temperatures again. And yes, it is of course known that we have a surrounding cooling water during the operational phase that is in direct contact to the cladding tube itself. So the spent nuclear fuel that is kind of also consistent of the cladding tube. The cladding tube takes then up the hydrogen due to the corrosion process at the temperature during the reactor operation, and this hydrogen ingress into the material. So it is of kind of interest what happens to this hydrogen during the interim dry storage phase within the metal, because probably you know that hydrogen has always an active influence to the material in metals in general. So what happens when the hydrogen is not in a solid state anymore is that it kind of precipitates in different kind of forms. So in the cladding tube itself, that has a tube form. It can precipitate in the form of circumferential orientated hydrides or in radial orientated hydrides. The difference is that the radial orientated hydrides have a more destructive influence to the cladding tube stability itself, so it might lead to delayed hydride cracking, for example. So the hydrogen, when it is in a solid state, starts to precipitate when it reaches a certain limit, so the terminal solid solubility for precipitation. And when this curve or this slope is reached, as you can see here in the diagram on the right, you might start to precipitate with the hydrides. On the other hand, you can also dissolute the hydrides again if you reach a terminal solubility limit for dissolution. Those two curves, they are not quite similar because you do have the hysteresis effect due to different energies that are needed for the precipitation and the dissolution process itself. So to give you an idea about the experiments and the setup is made at the KIT, related to also investigate these kind of effects and what happens with the hydrogen due to the temperature, pressure conditions in the dry storage phase. We make single effect experiments and we also have a quench bundle test. So for single effect experiments, we use original cladding tubes in general that have a height of about 2 centimeters. Also, we use other zirconium samples, tensile samples, and so on. And we try to investigate the influences of the texture on the grain size and the elastic strain. And we try to determine some diffusion coefficients of the hydrogen in zirconium and zircaloy. Also, zircaloy 4 cladding tubes, doublex and cielo cladding tubes are used for the investigations at the long-term bundle test at our quench facility in Karlsruhe. So the difference, for example, between zircaloy 4, as you might know, and doublex is just that we do have the same bulk material, but an additional liner in the cladding tube that contains more thin. So these are the materials that we use in general, and then at the quench bundle test, we would try to intimidate the interim dry storage conditions. So we do try to simulate the same temperature conditions, starting with 400 degrees at the central rod, and we try to have 2 different pressure conditions, 2 different hydrogen concentrations, and then in general we will have several different kind of setups. So before we start with our experiments, we need to hydrogenate our samples. So this might happen, for example, with our SICHA, the sievage chamber for hydrogen absorption, which we use for annealing from the gas phase. So it's just a kind of tube that is closed, and you can insert some hydrogen gas, and then the sample would take up all the hydrogen, which you can monitor with a pressure drop within this tube. This is, for example, a procedure in the furnace that we would use for small-scale samples. We do also have a larger furnace, Hockey furnace, that was great especially for the hydriding of very long rods, so, or let's say cladding tubes. So therefore we can insert 2.5 meters long cladding tubes and hydrate them quite homogeneously. Even though we just have a very homogeneous temperature in the central part of the furnace, because at the lower ends we don't have a specific heating anymore. Also the furnace is just 2 meters length. So yeah, at the central part we still get a homogeneous hydrogenation. So with this furnace we also hydrated 21 rods for our quench bundle test, which happens in a way that we always insert some hydrogen gas as well, but only from the inside of the cladding. So from the outside we have some oxygen gas that prevents any hydrogen release, and from the within we try to hydrogenate the samples always. This is then the kind of schematic illustration of how the bundle looks like with the different conditions of all the materials, all the pressures, and the hydrogen concentrations. You'd see that we have those 21 different claddings or cladding tube conditions as well, but then again, through the whole rod, we do have as well a pressure decrease through the ends. So we have different temperatures in one rod as well, which means that we will have several different results when the experiment is at the end. What we started with is a maximum temperature of 400 degrees in the central rod. As you can see, still at the central rod, we do have at the ends of the rod always a lower temperature. And then let's say the temperature decrease is about up to 20 degrees towards the other rods at the outer range. So what we expect from those simulations is that we can quantify any strain influences. So we expect the thermal influence to be the greatest, then the plastic influence, the cladding creep, and the elastic strain as well should be deliver some results. We don't expect it to be that great, but still the elastic strain has of course an influence, which you already tried to quantify with some small scale experiments. This is, for example, the facility that we would use for the small scale experiments and to try to determine elastic stress effects on the hydrogen diffusion behavior on the metal. So this is called interim facility, in situ neutron radiography camber with mechanical load. With this facility, we try to do tensile testings coupled with inductive heating. We can use conductless strain measurements and temperature measurements at the same time. And the big advantage of this facility is that it's transportable, so we can actually use it in all the external Newton B-plimes. It consists, because of that, just of iron-free components, so we try to avoid any long-term Newton activation as well. So you'd see here how the samples would be placed right in front of the scintillator when it is inside of the INCHAMEL facility. So basically you're not familiar with Newton radiography in general, I would say. This is why I just try to show you this small illustration. So what happens is that you would have an incident beam with a certain intensity passing through the sample with a certain thickness, and then you have the transmitter beam going to the detector. And with the Lambert-Beer law, you can then calculate the intensity that is left over. Also, you have kind of different effects. So the newtons can either be absorbed, scattered, or transmitted. So to give you a comparison with X-rays, for example, the difference is that the X-rays would interact with the electric or the outer shell of a nucleus, but the neutrons not. They would just pass through and would just interact directly with the nucleus. So you would have different images compared from X-rays and neutrons, for example. So we'd see this hard drive disk on the right. For example, the metals would appear opaque with X-rays, and then again you would see very much details when you investigate with neutrons. For example, organic materials would be then, on the other hand, more opaque with neutrons. So this is kind of the advantage that we use for our imaging experiments. So we try to see the hydrogen within the metal, because zirconium, as you might know, is basically the main component of cladding tubes. So if you would have a zircaloy cladding tube, for example, it would consist of 98% of zirconium, and zirconium is basically invisible if you look with it through with neutrons. And on the other hand, hydrogen appears as dark contrast, as you can see on the right upper hand. Therefore, we just need some calibration samples where we know exactly the hydrogen content. And with these calibration samples and the curve that you see on the left, we can then calculate the concentrations of hydrogen in any of our other samples. To show you some results, this would be, for example, a Circuloid 4 cladding tube on the left that was hydrated with zirconium hydride powder. So we tried to imagine how the hydrogen diffuses into the material. You'd see that, of course, the duplex material as well would behave quite the same. As I said, it's the same bulk material. Then you would be able actually to calculate some diffusion coefficient. So how fast is the diffusion in those cladding tubes? Also in respect to the, also in correlates to the diffusion direction or the actual directions of those cladding tubes. Just you need as well a time-dependent factor because the zirconium oxide forms directly in contact with air, which means before the hydrogen diffusion can start, we need to dissolute this zirconium oxide again, and then the hydrogen diffusion would start. But this is why we couldn't calculate any diffusion coefficients for these results, for these experiments, because it was ex situ, which means we tried to repeat everything in situ. And those are some results for the tensile tests we did, for example, with the zirconium tensile samples. You'd see, or you'd expect, because hydrogen always migrates towards the area with the highest stress, that at this point of region, where we have the highest or the smallest cross-section of the sample, we would have the highest stress, and then the hydrogen would migrate towards this region. This is what you can see on the right. We tested this with several pressure conditions at different temperatures, always trying to be in the elastic range. We couldn't see any influence so far, which is also due to the fact that we kind of had quite a long time to install our facility first at the beamline. So the time for experiments was quite short, but nonetheless, you see clearly the difference on the lower image that when we have a plastic range, so which would be the 400 degrees and 530 newtons, we see some or that the hydrogen moves. In this case, it was outgassing, but nevertheless, before in the elastic range, we couldn't see any changes, also due to the very slow timescales we had, so about maximum 1 day, which led us to the expectation that maybe it's just a local dissolution process and precipitation process that happens during the elastic stress application. But we still try to get new results. So generally, how would you determine hydrogen effects by elastic stresses on cladding tubes under conditions similar to interim dry storage? We do it with single effect experiments in combination with tensile testing machines observed by neutron radiography experiments, so in situ and ex situ. Also, we use a long-term experiment that imitates the slow cooling process and that tries storage relevant pressure temperature conditions, our quench bundle test. Also, definitely, which is mostly made is modeling, which is in fact one of the reasons why we do these long-term and single effect experiments, to gain parameters that are then used for the modeling process. And then, of course, you could use real samples to see what happened during the, some stress effects and the real dry condition behavior. So to give you a short outlook, we will continue single effect experiments, doing neutron radiography ex situ with the Ingemal facility for investigations of the stress influence on hydrogen diffusion solubility for much longer timescales than we did before. Also, we will repeat these samples to investigate the local stress-induced hydrogen dissolution precipitation processes. Then we will try to get all information that are possible out of the quench bundle test at the end, also with neutron radiography experiments and then metallographic investigations as well. also to see how the hydrides precipitated, in which directions, are they radially more or more circumferentially orientated. Yeah, so thank you very much for listening. And
so thank you very much, Sarah. So we have time for 2 short questions to that presentation, and who wants to make the start? Yeah, please.
Hi, Sarah. Thank you. Tom Makrowski, PsychLife EDF. Based on your research, what advice would you give to operator of interim storage in terms of making sure that the cladding behaves as it should? So what sort of measurement could we employ in storage to monitor the evolution of cladding of the fuel?
if I understood the question right, I would say, because for example, what we do is neutron radiography measurements, and therefore you'd need a neutron source. So it's not something that you can do back home. But it's the best way to see what happens to the hydrogen, or you can see visibly the hydrogen in the material itself. Otherwise, if you have the real application, so the real spent nuclear fuel in those hot cells, for example, I'm quite sure it's not so easy to see what happens to the hydrogen, because then you would need to get everything out and then have the fuel separated from the cladding again, and then have everything back in the hot cells, all those facilities, which is not really easy to handle. Our institute, for example, the INE, does that, so also related to the Spitzwurz project. They had real nuclear fuel, and the spent nuclear fuel was then investigated through their different kind of diameter. So after and before, they had the cladding separated from the fuel inside, and they didn't see many effects correlated to the stress effect, which is kind of part of this project itself. But generally, to get back to your question related to the operational phase, I cannot really give you a solution. I think that, for example, muon thing, this kind of research is more applicable directly in those repositories, for example. A neutron source wouldn't be so easy to install there, so sorry.
Okay, thank you very much. So this was a very deep answer and very interesting question, thank you. I'm afraid we've got no time for a second question. If our second speaker is here now? Yeah? Yeah, he is. Good. So I'll hand over. Thank you very much. And I'll hand over to Florence.
Thank you, Christoph. Yes. Thank you again, Sarah. So I have the honor to announce our second speaker for today, Leone Pasquato. He holds a master degree in mechatronics engineering from the University of Trento. He had a very interesting start. As a student, he worked in the automotive field and worked on electric race cars and worked in Fiat powertrain technologies as a software developer for engines, and also developed software for driving simulators. And in April 2022, he joined the Federal Institute for Materials Research and Testing, the BAM, and worked there as an electronic engineer and developed hardware and firmware for measurement systems. Please, the floor is yours, and you may introduce your presentation.
Well, thank you very much for the introduction. Today I would like to show you our development, what we are developing at BAM in the scope of the European project PLEIADES, which stands for Predisposal of Radioactive Wastes. As you may already know, low level and middle level wastes are stored, burying them inside a metallic waste drum and filling the drum with concrete. So our goal is to long-term monitor using battery-less sensors, the process of hardening and the evolution of the concrete itself over time, in order to indirectly identify potential defects such as corrosion or crackling of the waste drum. In order to do that, it's necessary to develop a technology able to transmit power and data through the metal layer of the drums, and also developing low power consumption sensors able to work embedded in concrete. In order to do that, we joined forces with VTT, which is a research center of Finland, and we split the tasks in two. We at BAM are responsible of the developing of the sensors, and VTT for the data acquisition part. So we developed this device called sensor node, which include two sensors inside, one for humidity and temperature and one for temperature and pressure. The idea is to isolate a small air volume around the two sensors and separate the volume from the concrete, from the external environment, with a porous membrane. So in this way, the membrane spore allow the water and gas particle to go through the membrane, while letting the liquid or the gas outside. And in this way, the internal volume can go in equilibrium with the external environment. These devices are kind of uniquely identifiable devices, and we can have up to 64 devices on the same communication line. Then we can place this device up to 6 meter water depth, so basically 600 millibars of pressure. And yeah, we have this kind of communication protocol limit about 10 meters. Yeah, and they are quite small, about 3 centimeters of diameter. To test the sealing technique of the sensor node, we did a small-scale test, filling a 40 centimeter height pipe with concrete and placing one sensor node on the bottom and also another sensor node outside. You see in blue the embedded sensor and the orange the external sensor. And after around about 2 months, the sensor is still alive, so it means no faults caused by leakages occurred, and also the measurements are compliant with the external environment. What we can see from the most right plot is the humidity. And of course, if we had add an air volume around the sensors and also a membrane, is like adding a first order dynamic system on the chain. So we are slowing down a lot the time response. So we basically took like 2 hours to saturate the humidity sensor, so reach the 100%. And the recovering time is very, very slow. And as you can see, after 2 months, we are still more than 80% of humidity. It may sound strange, but it's kind of compliant with other tests we did in the past. And yeah. Then the sensor nodes are not the only part of the measurement chain. We aim to embed 5 sensor nodes inside a drum and which they are connected with what we call an embedded RFID unit, which is basically the electronics embedded in the drum needed to receive the power and transmit back the data. The embedded RFID unit has a twin on the external side of the drum, which is connected to the master device we call the microcontroller unit, which is the device which master all the measurement routine, so control the power transmission and the data uplink. And it is possible to store the data locally as a file or interfacing with a cloud platform. Little bit more in detail in the power and data transmission. In the external and embedded units, there are two UR ferrite antennas, like the one in the picture, and they must be symmetrically placed, one in the inner and the other one in the outer surface of the drum. And of course, the efficiency of the power and the data transmission are limited by the material between the two antennae. In this case, is steel. So there are electromagnetic properties, and the power transmission is quite low, but still enough to power and control 5 sensor nodes inside the drum. Of course, to work, it's using super low frequencies, about 100 Hertz. In fact, when they are placed and mounted on the metal drum, when they are powered, you can hear the noise. That, in any case, lasts about 30 seconds, which is the time required to charge the internal capacitor and collect the data. We did already an integration of the data acquisition system and our sensor at BAM, and you can see from the plots that the blue curve are the data collected by the embedded unit. So they are like, as you can see, 5 waves more or less, which are the binary data of the sensors. The red curve are the analog signal detected by the external antenna, and the green one are the reconstructed binary data from the external device. So yeah, this is it. What we are doing now is to prepare an official demonstration for the PLEIADES project, which is to basically repeat that installation and filling the drum with concrete and connect with the cloud database upload. And VTT itself will also show its RFID system at TVO by the end of the year. This is it. Thank you.
Thank you very much. Are there any questions from the audience? Please.
Yeah, Mike Weber also from DAM, Division Safety of Storage Containers for Radioactive Materials. My question is, what is the special motivation for that project? What is the waste where it is what it is foreseen to install? It is in the area of low and intermediate level waste, where cemented waste is a big issue.
Yes, yes, exactly. Mostly the PLEIADES project deal with low level and middle level wastes. So yeah, there are many work packages inside this the project. I work in the one which is developing actually measurement system. For example, other partners are developing sensor to be used outside the drum to detect the radiation. But more specifically, my part is just to monitor the the state of the concrete used inside the drums. Yeah, exactly. The idea is to combine the real measurement data with a digital twin developed by another work package in order to make prediction about what could happen, what chemical reaction could happen in future, and yeah, indirectly maybe detect corrosions or cracklings or similar things.
Thank you very much. Are there any other questions? So, thank you again.
Thank you.
So this is maybe the mostly detached talk from the topic of this conference. But still, I want to attract your attention to this topic, what from my point of view is extremely important for such deposits, what you are going to do, and what should be, from my point of view, strictly addressed. What does mean seismic reflection-based approach for determining permeability? So we know that the permeability is the key factor for safety of nuclear deposits. And but if we estimate permeability from one borehole and then estimate permeability in another borehole, then it doesn't mean that we know the permeability between them. Yeah, and so the seismic methods, they are usually used to make interpolation between boreholes. But the point is that seismic methods, they don't show permeability. They show reflectivity, and maybe the best what they can show us, these are seismic or elastic properties. So these are seismic velocities. And so the bridge here is between permeability and seismic methods is from reflection seismic methods and from seismic images to get seismic velocities, from seismic velocities to get the next thing what is important for permeability, this is the porosity, and then from porosity to conclude about the permeability and try to make a kind of interpolation. This would be a way. Okay, so we did a couple of works in this direction. There are some publications, and I hope they are visible in the file what is attached to my abstract. And so the main idea of what I'm going to sell you is the following. So basically, the porosity on the pore space in rocks has at least two components. The first one is such kind of stiff pores. And another one is a kind of compliant pores, what are cracks and also contacts between grains and such domains. Yeah. So why they are stiff? Why these are stiff? Because if you compress the system, they do not deform a lot. But if you compress the system, these things will deform a lot. Yeah. And so basically. So these two components of the pore system, they impact seismic properties in a different way. So these ones do not impact seismic properties too much. But these ones impact seismic properties very strongly. So now it is clear that the logic should be, if we want to conclude from seismic properties to permeability, we must understand how permeability is impacted by these two types of the pore system. So by the stiff one and by the compliant one, yeah? Because they are then correspondingly reflected in seismic properties. Okay, so this is just one of results of considerations what we did for such type of systems. So basically, the porosity, the total porosity, can be represented as function of stress. For example, think about confining stress, yeah, as a function of stress as the following one. There is a part which corresponds to the stiff porosity, which is a linear function of the stress. And there is a part which corresponds to compliant porosity, and it is an exponential function of stress. And so basically, if we take a rock sample and load it, even in 3-axial experiment, then we will obtain a tensor of 21 elastic parameters, and they all will be functions of stress. But there will be here two impacts or two contributions. One contribution will be from the stiff porosity. This will be this one, a linear kind of contribution as function of stress. And there will be these exponential parts, which are describing the contribution to elastic properties from changing or from closing compliant pores. Yeah, so one can try, or one have a possibility to distinguish between these two things. Okay, and for example, in one of experiments, which was done, by the way, by Sibylle Meyer, who asked the previous question. So this is a sample of a shale. I think that this is even an Apollonius shale, but I'm not sure. So this is a orthorhombic anisotropic rock. Yeah, so orthorhombic anisotropy. So if you know the orientation of this sample, then what we have, this is 9 independent elastic constants, what we must work with there. And this is how, using this type of representation as functions of porosity, of compliant and stiff porosity, one can describe the behavior of the elasticity of these elastic properties as function of stress for this sample. And you see that this is quite a good representation. So one can really describe what is going on in rock if we know if we can differ between stiff and compliant porosity. Okay, these are elastic properties. So this is what seismic will give us if we do a good seismic. Okay, now let us go to permeability. So we know that permeability, this is a very difficult quantity. It is hard to combine or to connect it to something, but people try to connect this to porosity. So this is a type of functional dependency of the type of Kazeni-Karman. Yeah, so Kazeni-Karman, just a kind of proportionality to a power law of the porosity. However, we know that that porosity has two components, stiff and compliant. It would be great to separate them. So why not to think about permeability as a function of these two components of the pore space, of the stiff and of the compliant one? For example, let us go now to a simple models and try to find a kind of proportionality coefficient times stiff porosity plus proportionality coefficient times compliant porosity, power something, or this type of functions. So how to establish these models? So it is clear that if we would be able to establish this type of dependencies of this type of models, then having from seismic information about porosities, stiff and compliant one, we can try to predict permeability. Okay, of course, this would be not an extremely very good job, but at least something. Okay, so let me show you how to try on some samples. These are some samples from the Perm region coming from the time when we have cooperated with Russia. This was something like 5 years ago. And this was published, by the way. And so just I show you how to try to understand what is the function of permeability connecting, bridging between permeability and the type of porosity. So let us make an experiment. We consider porosity as function of, for example, confining stress. And we consider also permeability as a function of confining stress. So this is in one of samples. There was sandstone in those situations. What we see here, that the porosity behaves so exponentially, and the permeability seems to behave just linearly as function of confining stress. So what is going on? So what exponentially here, what is responsible here for this exponential behavior? This is the compliant porosity. So this means that from this situation, it is clear that porosity behaves exponentially, at least in this situation, so in this part of the stress of the load. But permeability behaves just linearly. What is going on? The response is clear that in this case, for this sample, permeability is controlled by not by compliant but by stiff porosity. And then corresponding model then reflects this. So another experiment. This is another sandstone. This is behavior of porosity, behavior of permeability. This just, again, here porosity, here permeability. It is clear that permeability is porosity exponentially decreasing, here up to a kind of constant level, and permeability also exponentially decreasing. So in this particular sample, the permeability is controlled by compliant porosity. So this is just the corresponding result. So, or another sample, this is a limestone in this particular case. Again, so this is the porosity. You see here exponential decrease, then linear. But permeability doesn't care about the exponential part, and it is a linear part. So this means that permeability is controlled by stiff porosity. And finally, one more example. Again, you see here porosity and permeability both having an exponential type of behavior. So this control of permeability is here made by compliant porosity. So we, if you collect, for example, for a given field, so in this particular case, this was an oil field. If you combine for an oil field all this information and then look at the samples which are representing the end members of this situation, then you will have samples which are controlled by the, this is the porosity, this is permeability, and all these signs, these are just for various compliance stresses. So this is just a plot which combining different various samples and corresponding stress dependency of permeability and porosity. And then for end members which are controlled by the stiff porosity, we see a very clear dependency of permeability on porosity. And here we also see such a dependency, but it is these are samples where permeability is controlled by compliant porosity, but firstly the porosity is very small and stress dependency is huge. Yeah, now if I know what are end members, then I can easily go and try to interpret seismic results of seismic data, for example, of seismic tomography, and try to interpolate for permeability. But if I don't know what is this here, and if I have a kind of mixture of samples, simple samples with mixed lithology, then I will have a kind of chaos here. Yeah, and I will be unable to interpret anything. So basically, there is here one more very interesting aspect in all this business, that the permeability can be very anisotropic. If we go to samples with permeability which is controlled by cracks or compliant porosity, then we can have a kind of such type of dependency of permeability on directions. So we have a very strong permeability anisotropy. This permeability anisotropy is also related to seismic anisotropy. But it is interesting that the permeability anisotropy will be controlled by terms of this order, and seismic anisotropy will be controlled by terms of this order. This means that seismic anisotropy will be significantly smaller. But this means from other side that if you have small seismic anisotropy, it doesn't mean that you will have small permeability anisotropy. It can be huge, yeah, because you have here very different power laws. So basically, let me show the concluding slide. So what I think is important is this is the understanding of permeability as function of the pore space. Is it controlled by the stiff pore space, or it is controlled by the compliant pore space, or it is controlled by a combination of both of them? It is important to build a model. So, but what to do to build a model? This is not to go this conventional way, seismic velocity, porosity, permeability, but one should go into laboratory, unfortunately, and do a lot of work on samples and understand your lithology. And then from this, construct models of permeability, and then from them, conclude what type of porosity controls your permeability. And then after this, you will be able to go to and construct models for seismic velocities. And then you can invert seismic velocities for stiff and compliant porosities, and finally for permeability, and by the way, also for the pore pressure. So thank you.
Thank you very much for the interesting talk. I expect there are some questions from the audience.
Hi, I'm Hamelidos from the French branch of Inter Group. So I'm not familiar with stiff and compliant porosity, and my question is, what is the relation with efficient porosities that have a main impact for permeability?
Okay, so basically, again, so you can think about stiff and compliant porosity like about fractured porosity and domains close to contact. So basically, this is pores with aspect ratio of 0.01, something like this. And stiff pores, these are kind of oval-like or round-like type of pores with aspect ratio close to 1. And for example, in sandstones, you can have such relations like 10% general porosity, 0.1% or 1% compliant porosity. If you go to granite, then you can have all porosity to be the compliant one. Yeah, and if you go to shale, that's already a difficult question. Yeah, so this is very difficult. But in shales, basically, you have huge amount of, sometimes, huge amount of stiff pores. So, for example, all these gas shales, all unconventionals, they have huge stiff pore spaces, but they are isolated. So the permeability can be controlled by the compliant one. Yeah, so cracks and so on. So this lithology is interesting and complex.
Thank you much. Maybe there's a short question. This is not the case. Thank you very much, S.A.Shapiro, for this nice talk.
Thank you.
Then we will come to the next talk, which is given by Jens Birkholzer. He did his PhD in 1994 in Aachen, and since 1994 he is also in Lawrence Berkeley National Laboratory just for a short break of 2 years. He was back in Germany, And now he's the director of the division Energy Geoscience.
Thank you. So we're going back to faults. Thank you, too, for giving some nice fault geomechanics intro, so I can be faster on that. I will be talking about some experiments we did in situ on a fault in a sort of shale argillite unit, in fact, the Opalinos clay in Switzerland, in order to figure out whether pore pressure increases in the fault could lead to permeability, and that, of course, would be a concern for, potentially concern for radionuclide migration. So this is sort of a sketch of what we might be leading to pore pressure increases. It could be temperature dependent, where you have the thermal expansion and you could create pore pressures, or long-term gas generation from corrosion issues could lead to that. So are we changing essentially the slip tendency in a dynamic sense from a stable system to a reactivated system? And I'm gonna not talk about the mechanics that are shown here, but essentially we're interested, let's say we have a fault that's not slipping because there's a lot of confining pressure on it. If you inject into that, or if you increase pore pressure in it, you push against that confining stress and you could actually get reactivation happen. We know that happens from other geosciences disciplines, let's say the wastewater injections that occurred in the mid-continent in the US in a crystalline basement. Magnitudes, seismic magnitudes of more than 5 were generated. Seismicity generated was, in fact, more frequent than in California in a initially fairly seismically non-active zone. So we have to be concerned about that. We have to understand it. And we do understand quite a bit in these hard rocks. What we didn't know when we started the experiments is really how softer sort of faults in softer units would behave, and particularly faults that are initially pretty much impermeable, which we have in the Opalinos clay, for example. So what we wanted to get at in these experiments is sort of a fundamental understanding. That's bullet one. Secondly, the question, can we generate permeable pathways and for how long? Because at some point the hydraulic driving mechanism will probably go away. Will there be some observable seismicity, or will it be largely aseismic? And then finally, what would be the performance implications of that? We decided to go into an in situ experiment, and we were lucky to find this beautiful fault in the Monterey Rock Lab, which is in Switzerland. It essentially a system of tunnels that cuts through the Opalinos clay. You can see here there is a fault that actually cuts through some of those tunnels, so you have direct access to the fault. You can look at the structures, you realize the fault is really not a simple plane. It's usually a bunch of sliding planes potentially. There's a damage zone, there's slick sides, there's some core sort of material, gouge material that acts geomechanically different. All of that complexity we were trying to capture in the experiments. The fault itself isn't super large, so you would probably in an early site characterization be hard-pressed to find it even in a deep setting. 10-meter offset, maybe a few hundred meters in extent. So what we then did is we drilled from the tunnels through the fault. We had essentially a 2015 experimental campaign, which was about 30 meters, maybe 40 meters below the tunnels, fairly small, just a few meters between injection and monitoring. And then later in 2020, 21, 23, we went deeper and into a larger fault patch. And also added a bunch of additional monitoring. And in between, we did some long-term sort of, we stopped injecting, and then we kind of checked what the fault would do in terms of post-activation behavior. A bunch of partners. Some of these partners, in fact, have nothing to do with the nuclear waste world. They were interested in that because of questions about CO2 sequestration. These rocks are also very interesting cap rocks, sealing units for that, for natural gas storage also. So this is the setup. As I mentioned, we drilled into those faults, and then one of the tools that my colleague Yves Guglielmi developed is shown here, which is essentially a packed-off system. You kind of drill through the fault, you clamp it at the bottom and the top, and you have a deformation cage here, which gives you the three-dimensional displacements, gives you sort of rotation as a function of time at very high resolution, both in time and space. So as you put that into this cross-cutting through the fault, you inject. At the time, you measure flow rate, so that tells you something about permeability. You measure pressure, you measure the deformations, and you can use that both in an injection sense, but you can also place it in a monitoring borehole and basically do this sort of without injecting, just sort of in passive mode. We used that in the first experimental series and in the second, in the larger test bed. In the second, we did something else. We realized that in the first pass-through, we only had these single monitoring points, and we wanted to know more about the 2D or 3D behavior. So if this is the fault, we had boreholes that were then drilled above and below the fault and sort of few meters away. And we did active seismic through that fault. Again, we call it CASM, continuously active seismic. So every minute or so, you have these sources shoot, and then you have receivers on the other end. So we could essentially get a time-lapse seismic picture of what changed as we were injecting here and as the fault was slipping. These are just some graphics of the experiment in the tunnels in Monterey. This is the deformation cage here. It goes into boreholes, a bunch of typical experimental lines here with measurement, the pore pressure measurements. And we could actually, once it was installed, we could run it from Berkeley, which was really nice. This is the first experimental cycle. So this is basically a cross-section through that fault. We had one injection point here, a few meters away. We had a monitoring point. Both of these equipped with that sensor I talked about. And then we typically did sort of short-term 30-minute cycling. We increased stepwise the pressure in that chamber. And then stopped, increased a little higher, stopped a little. And then in the third round here, we were in fact getting a breakthrough. So initially there was almost no permeability in that fault. We got a breakthrough shown here. So these are displacements in the injection chamber, so tiny displacements here. Nothing in this monitoring chamber, then suddenly it shoots up. And in fact, a little later, we generated a minus 2.3 earthquake, which we didn't quite expect. So we'll look at this event in a little more detail in the next slide. So here, first of all, we looked at what kind of permeabilities might have been generated, and we did calculate that from the pressure fall-off as we stopped injecting stepwise. And you can see that the initially very low permeability, and this is sort of first-order estimates, did increase quite a bit. And particularly when we had this breakthrough, we got probably 5-6 orders of magnitude increase. So that could be performance relevant if it was to continue over time. Zooming in a little more, we're now just looking at the third cycle. And you see in blue, again, the pressure in the injection chamber. And you see that at some point here, we suddenly get a lot of inflow. This is a pressure-triggered experiment or a pressure-controlled experiment. So we got this sudden pressure drop because permeability was developed. And then the system wants to push fluids to keep the pressure at that level. And then in light blue, you see that now we got breakthrough here. And a little later, another pressure drop here as if something further out happened in terms of permeability generation, and then this earthquake. We could look even more closely into just this sequence when we generated permeability. This is the flow rate into that injection chamber. This is the pressure here. We can compare that when we first see displacement. So this is a little bit of a displacement here, which then goes up. This here is later a little bit of displacement here. And if you pay very close attention, you will see that this initial early displacement really triggers a little later permeability happening. Once that happens, we usually get somewhat later even more displacement and then even more flow. How much more time? A little more time? Oh, okay. All right. So this is the second experiment. So I'm jumping experiments, and what we see here is just how the geophysics worked. This is the projection of change in P-wave velocity projected onto the fault. This is the injection borehole, about 10 meters in this case, so larger patch is a monitoring borehole with that sensor again, another monitoring borehole here. This is injection 2, and we see that we have triggered some changes in the P-wave velocity decreases, but they haven't broken through. And then here in injection 3, we actually get some breakthrough in this direction, but not in this second monitoring borehole. We can now look at the measurements in these B1 and B7 sort of sensors, and we get again this very early, quick initial activation mechanically right here, followed by faster displacement in this one, and we don't see anything in this area that's not hydraulically connected. So again, it looks like slip precedes fluid propagation, which in turn may trigger further fault opening and then finally flow in that fault, which is not typical for faults that have some initial permeability. Just to take a quick look at the long-term behavior, so we did some pulse testing every few weeks or so after that first experimental series in 2020, over 2 years. You see that, so we stopped basically injecting a lot in order to trigger. We just did these little injections, and that tells us something about the permeability. So once the pressure goes down, you get the rapid permeability increase, which is good. It doesn't go all the way back to the initial, which is somewhere down here. We see some evidence of long-term, call it sealing or maybe healing. So definitely something is happening in these weak clays, and we're still observing that. Just some sort of summaries here, and in terms of what we think we learned, we're still investigating, but it looks like that the paradigm of how faults reactivate that have sort of more argillite type, shale type behavior, that you really need to have some local slip initially to get some fluids into those faults. And once that happens, then you create a bit of permeability, you open that fault patch further up, and then you really get permeability to flow, and potentially more slip and rupturing happen on a larger scale. We haven't seen a lot of seismicity, so most of that is aseismic, but we did see some, and we observed a rapid permeability drop followed by some slow sealing and healing, which we're still measuring. And I believe I have a little more time, right? So I wanted to talk about a next step that we're planning in that same test bed, because all the sensors, the tools are still there. We are now interested in doing a thermal slip experiment, and we're starting some feasibility studies pretty soon. The reason is that, A, we wanted to figure out whether geomechanically, and we know it will be geomechanically different if non-isothermal fluids are injected. And then how that would also affect permeability evolution. But secondly, instead of injecting directly into that fault, which is not really what would happen in terms of a nuclear waste repository, right? We're not injecting into a fault here. We will have a borehole a few meters or so with a heat source that heats up the fault, but the pore pressure will have to come from the rock, and that will be a different driving force, which we still want to sort of understand. And if I have another minute, do I have another minute? Okay. There's some different study that we're doing. This is not Opalinos clay. This is actually in California near the San Andreas Fault. Here we're not injecting fluids. What we're interested in here is whether a major earthquake nearby, let's say kilometers, 20, 30, 50, 100 kilometers away from a repository, so some seismic wave that moves towards that repository, whether that could and what type of fault reactivation that might trigger. And this is of particular interest to the Japanese program. So what we essentially did is create a test bed about a few kilometers away from the San Andreas, but these are separate, smallish faults, similarly equipped with displacement sensors and some other seismic measurements and surface creep meters and whatnot. And then we let that system sit. So we installed that in 2020. Of course, when you wait for something to happen, it doesn't happen, except in 2023, in April, there was a 4.4 earthquake on the San Andreas, about 50 kilometers away, which we were able to measure at our site, both in terms of some of the seismic wave, but also, and that's the interesting part, we never really had that, in terms of the displacements from this displacement sensor that I described earlier. So we got some measurements of time-dependent and directional slip opening of that fault, and this is sort of the, in the micrometer scale or so, hard to read, about 20 or 25 micrometers. We're still making sense of that, but it's really an interesting data set. It's just super exciting, so I thought I wanted to mention it. And with that, I'm done. Thanks.
Thank you for this very fascinating talk. And maybe two quick questions.
Yeah, thanks again. Wolfgang Wartenberg from BASE. Just a question. You stressed out the slip component within your method. And how convenient was it that you were actually testing on a former thrust fault with the movement?
How convenient was it? Well, I think we took what we got at Monterey, but it was convenient. Thank you. Yeah.
Then one last question.
Thank you, Jens, for this great insight into the fault slip experiment. The question is there something can be learned for the selected repository in the same formation in Nördlich-Legern, a completely different stress field, but the same Opalinos clay? So is there something which can be transferred to the selected site? What are maximum pressures allowed in the repository, something like this? Or is it difficult?
Yeah, I think there's a lot to learn. I mean, I didn't have time to talk about it, but there's a whole sort of modeling effort and sort of what kind of constitutive laws would best describe that behavior. And I think we can definitely translate that to different stress conditions, different geometries, and obviously we probably want to test it at some point. If Nördlich-Legern builds an underground research lab, we could probably do the same thing there, right, in 900 meter depth. I think the other thing to keep in mind is that at the end of the day, we want to translate it into performance impact, and this is more sort of fundamental research still, and that translation that still needs to happen. But at this time, the fact that we have sort of fault closure and permeability reduction after the pore pressure pulse is gone is probably good news, because most of these repository-induced effects will be early, but most of your concern about radionuclide migration will be much later. So if you can demonstrate that, and healing and sealing is in fact fairly effective in those type of rocks, then you might be fine. You will be fine, probably.
Thank you.
Hello everybody to this session on nuclear decommissioning and waste minimization. The session will be chaired by Mr. Ridao. He's from the Karlsruhe Institute for Technology, and it will be chaired by me. My name is Bernd Rees, and I come from the Federal Office for the Safety of Nuclear Waste Management. Waste and residual material management is a very important task for decommissioning projects. For example, light water reactors. The controlled area ranges up to 200,000 megagrams, but only a small part of it, estimations say about 2% of it, will become radioactive waste that needs to be disposed of. So how does it come to this? And one reason for this is that the tools for the radiological characterization, for the cutting, and for the decontamination are available for dismantling. But optimization of these tools is still a field of research. And so I'm looking very forward on the presentations we get today, here today. And I would like to hand over to Mr. Ridao, who will give some introducing words to the institute where the presenters today come from. Mr. Ridao.
Thank you very much, Dr. Rex. So thank you very much, everyone, for coming to this presentation. So as a brief introduction of myself, I am a French-Spanish civil engineer holding a master's degree of the INSA Toulouse in France, as well as architect holding a master's degree from the University of Seville in Spain. Since 2020, I have been working in the Karlsruhe Institute of Technology in the Department of the Construction and the Commissioning of Conventional and Nuclear Buildings in the Institute of Technology and Management in Construction of the KIT. All the presenters in this session come from the same institution. We are located in the campus south in Karlsruhe, where we have our competence center, where we do research in all aspects related to the commissioning. So I'm giving the floor to the first presenter of today, Mr. Kazemi. So Mr. Kazemi is a mechatronic engineer. He finished his master's degree at University of Hanover, and now he works in KIT, at KIT. The title of his presentation is Development of a Robotic System for the Automation of the Decontamination Process of Nuclear Power Plants. So Mr. Kazemi, the floor is yours.
Yeah, thank you very much for the opening words. My name is S.Kazemi, but you can call me Sia if you want, just like the singer, but if you want. Let's look at the agenda. So I will introduce you first the project RobDecon in its second phase, and then that's a laser pointer, yes. Then I jump to the introduction of our closed chain for decontamination. It's a part of project RobDecon. We have a lot of friends. We are one part of RobDecon, and then in our closed chain, we have two robot systems. The first one is GammaBot. I will come to the robot GammaBot again, and the second system is DecontBot. It's a robot system for decontamination. That's why we call it DecontBot. We also have two tools or end effectors for our robot system, milling tool and a contamination array. So I start with the chain and then GammaBot, and then I will introduce you the two end effectors, and I will come back to the DecontBot because it's the main part of, it's the heart of this presentation. So very shortly about the project RobDecon. The goal of the project is to develop, the RobDecon is, the project is about for building and developing of the robot system for decontamination of hazardous environment like nuclear power plant. The project has been started at December 22nd and will end at December 26th. Our partners are Fraunhofer, IOSB, DFKI, KIT of course, FZE, University of Applied Science in Karlsruhe, and industrial partners are Göttingen, Kraftanlage Heidelberg, and ICP. So our closed chain for decontamination. We start with GammaBot. This is our first robot system. It's a smaller robot system, maybe like this, for autonomous environment exploration and radiation measurement. This robot system provides us necessary information, geometrical and radiological information for the next steps. And then the second step, we use the point cloud information of the GammaBots and build with little magic, I would say. We build a beam model to improve the model and get rid of obstacles and noises to improve the model, and also put the contamination information to the geometrical model. For example, this is the model of our living lab, and we see that in this wall we have a hotspot here. And then, based off this information, so we build a second robot system. That's my job. The second robot system, there's a decont system. Decont bot must be an automated system. And the task of this robot system is to put these two end effectors on the right position, the milling tool and the automated contamination, also the contamination array, the tool for to measure the contaminated area to see if it's clean or not. So this is our GammaBot. It's a differential kinematic robot system. It's I would say it's a quite flexible robot system. It has various sensors. For example, you see here a 2D LiDAR sensor. We use this LiDAR sensor for build a 2D map from the environment or from the room. It has also a 3D Faro laser scanner. It's provided us with 3D point clouds from the whole room, not only 2D, also 3D. Also a scintillator probe to measure the activities and detect the hotspots. Yeah, and also it has also an interface with ROS, the robot system. ROS stands for Robot Operating System. It's a common interface used for robotics. It's a Linux-based interface. So the first tool or end effector that we develop is a milling tool. You see the milling tool has 2 degrees of freedom, or 2 engines, 2 motors. The first one is the motor for the milling process itself, the milling head. And the second motor is the smaller motor for the lateral movement of the milling head to right to the left and left to the right. So this, the tool which we control with a PLC, and this is the electric cabinet, has this is a lot of sensors. For example, it starts to work only if it has is attached to the wall. So it's because of safety reason and also save energy. And here is the battery of the system. The second end effector that we create is the contamination array. It has 4 measurement systems to measure the surface activities. It also has a linear unit for movement of these 4 measurement system up to down and right, left to the right, and also has various sensors for the measurement of the position of the device, which we use for the documentation. So this device also generates automatically the documentation, the positions and the measurement values. So finally, we got the decontamination system, the decont bot. This is our decon system. It's just a very normal platform. It's not a robot, no automation. It's just this very normal platform controlled by a joystick. We chose that this platform as our base to position these two end effectors. It has a vehicle, so it's just the mobile part, and also a manipulator with 3 degrees of freedom. It has a height of about 2 meters, and with help of this linear unit and the arm, it can reach up to 8 meters. It's quite good. So the platform, we equip the platform with necessary electronic sensors, controllers, and safety systems to make it a real robot system. So automation concept. So as I told you, that the system needs necessary electronic device like controller. So the task is, what should the robot system do? First of all, we have a power plant, a room, or a place. So the robot system, the vehicle of the robot system needs to go to the target wall. So now that the manipulator is the right position. And after that, the manipulator needs to position the end effector at the right place, at the hot spot. For that, we want to create this control loop. So the idea is we know how the environment looks like because of the gamma bot and beam model. So we calculate the desired trajectory, the best way from A to B, so if you want. So the desired values, the desired trajectory. We measure the real position of the robot system using sensors, and then the difference between desired values and the real values is the so-called control error. So the controller says, give the error to me and leave the rest for me. So the controller gets this error and sends the proper commando to the actuators, and the goal is to minimize this error, which means the robot needs to go exactly to the desired trajectory. So for that, we want to build the electronic cabinet for the original platform. As a central control system of the platform, we have a PLC from Bosch Rexroth. It's my favorite company. So we need some sensors to measure the position of the manipulator. It's a 3 degrees of freedom, so we need to know the position of the manipulator. So the sensors that we have, they speak can open. It's a communication protocol. We translate the signals of the sensors using a gateway to EtherCAT and send the signals to the EtherCAT master or the PLC. We also control the motors of the platform with the same gateway because it also speaks, the motor controllers also, they speak can open. We have also, of course, LIDAR sensors or LiDAR sensors for the localization of the platform. And they send, they say the data to the localization PC, and the localization PC uses this information of the LiDAR sensor and sends the real position of the vehicle to the PLC. We also have a safety system, some kind of safety sensors, and the safety sensor sends the information to another PLC or CPU. This CPU here is only responsible for the safety, if the situation is safe or not. If this situation is safe, then the platform can move. Otherwise, it has to stop or looks or search for another way. So how we measure the positions of the for the platform? For the position of the vehicle itself inside the environment, we use 2 LiDAR sensors. We put them diagonal because it sees in this way better. And the two LiDAR sensors, they see the environment. They compare it with the card that we have. It's a real card of our real map of our living lab. And then they compare it with the card and then sends the best approximation of the position to the PLC. For the measurement of the value, to measurement the position of the base and the telescope, we use wire DROS encoders, and also for the measurement of this angle here for the arm, we use two tilt sensor, inclination sensors, one here and one on top, and the difference of these two sensors will be the position of this joint here. So that must be a video. I don't know how can I start it, but in this video, this is our PLC program, and you see here that we have the sensors information inside our PLC, and we are very happy with it, but I don't know how we can start this video. Okay, the values are there. So the next slide. We have also shortly about our safety concept. These LiDAR sensors that we have, they are not only for localization, also for safety. They can see people up to 9 meters, and if one person is there, then they send a warning signal to the PLC. Oh, sorry. We also have safety, so-called switches. The platform can only move if the manipulator is in home position, because when the manipulator is in home position, it's very unlikely to keep for the platform to turn over. We also have inclination sensors, because we measure the tilt angle of the platform, and if it's more than critical threshold, then the platform cannot move anymore. We also use 2 sensors for every degree of freedom, 2 sensors which work with different measurements functionality. So it's the better safety system to use 2 sensors with different kind of functionality. So this is also a video. Oh, it's on. So you see in this video our safety system in action. The motors are running peacefully. The LiDAR sensor sees a person, so it stops working. The switches, when I cut the switches, the motor is not going to work anymore. And also the inclination sensor stops now and again, and now it stops again. And so our safety system works. Nobody is going to be hurt. But I have one sensor here in this, one tilt sensor in this video, but we have 2. So for communication with gamma bots, I told you we have 2 robot systems, and these 2 robot systems need to talk with each other. They need to be friends. The gamma bot provide us two types of card, the 3D card, the 3D map with this laser scanner, and the 2D card with the LiDAR sensor. First of all, for the localization of the platform, the 2D card is more important. So the card provided by, created by the gamma bots is a ROS format card, which means it's only suitable for robot operating system. We converted the card to the suitable data type, and also image processing. Image processing means, of course, filter the noises and filter the noises in this case. And then we put the cards, 2D card, to the localization PC, and the localization PC gets the sensor data, compares the sensor data with the card, and sends the position to the PLC. So the PLC can work, and the system can work automatically. We also send the position and the card, original card, to the control cabinet only for the visualization, so the users can see what's happened there. So for the visualization, so we have a GUI for end users. I chose the PLC software, but users don't need to work with line of codes. They need to work with buttons, for example, stop, start, or something like this. And to see the position and the situation, the user can use two interfaces. The first option will be then a web-based interface. You just need to put an IP address to your browser and then see what's happening here. Again, that is our living lab, and here is the machine. So you see that's the position of the machine in our room. Otherwise, if you don't want to use this web-based interface, you can use RViz on ROS. RViz is a visualization function of ROS. So you can also see almost the same results in RViz in your Linux system. So as a short summary, okay, summary must be short. As a summary, that's the whole work that we need to do. We connect the manipulator sensors to the PLC. We connect actuators or motors to the PLC, to the same PLC. We connected LiDAR sensors to the localization PC, and we send the positions to the PLC. It's also done. We created the safety systems, and the safety system has its own local safety PLC, which is only responsible for the safety. We also converted the 2D cards from gamma bots and imported into the localization PC. Now we need to assemble all the components on the original platform. That so means we need to put all the electronic to an electric box and touch it somewhere on the platform, and also mount the sensors. I'm also working on a user-friendly GUI. As I told you, no one wants to work with line of codes. So I'm working on it. And after that, after this step, the device is, you can call the device a real robot system. And then I'm going to implement a control algorithm on it, because then in this case, it can work automatically. And then also trajectory planning based on 2D and 3D map. Trajectory planning means we have the 2D and 3D maps. We want to calculate the best way from A to B or B to C. So thank you for your attention. If you have any question, I'm here.
Thank you. Thank you very much. So any question?
Maybe just one question. You mentioned before that you are constructing two robots who need to communicate with each other. A really simple question, why do you building two robots? Do you have to do it, or are you doing it because of, for now, to make it simpler?
Imagine the first robot system, the gamma bot, needs to scan the whole building. And the nuclear power plant it's quite big. So you can, the second robot system, the decon bot, is about 4 tons. You can send a 4-ton robot to the whole power plant to scan the whole structure. You need a smaller robot system which is faster, send it to the whole nuclear power plant. It tells us where we have contaminations, the hotspots, and then we send the robot system only to the second robot system, the bigger robot system, only to the hotspots. Basically, it's possible, but it doesn't make sense.
Any other question? So thank you, Mr. Kazemi. I am presenting the next so the next presenter is Mr. E.Rentschler. Mr. E.Rentschler is a civil engineer who worked as a construction site manager and found his way back in science in 2020 at KIT. He works now in the field of the construction and dismantling of nuclear facilities. And the title of his presentation is Econt 2, Advancement of a Demonstrator for Dry Mechanical Decontamination of Corners and Inner Edges in Nuclear Facilities. Mr. E.Rentschler, the floor is yours.
Hello and welcome to my presentation. As said, my name is E.Rentschler. I'm also from KIT. And the title is quite long, so we made a shorter one, Econt 2. But the full title, for once you heard it, Advancement of a Demonstrator for Dry Mechanical Decontamination of Corners and Inner Edges in Nuclear Facilities. First of all, I want to give you an overview over my contents. Special thanks to the Federal Ministry of Education and Research and the GRS for funding this research project. And let's dive right into it. So first of all, the project partners. We have 4 project partners, 2 of research, 2 of industry. As said, we're part of it, KIT, we're partner for research, we're focused on design of the test benches and experiment series. Then we've got another partner in research, the HTWG Konstanz. They're focusing on the mechanical engineering and design of demonstrators. Then we've got the industry partner Contact. They're experts in concrete surface work and diamond cutting. And our nuclear partner Kerntechnik, nuclear industry partner and expert in nuclear dismantling, decommissioning and decontamination. So first of all, some basics about the Econt project. As the title is Econt 2, there was a Econt 1. The title of that was Development of an Innovative Semi-Automated Demonstrator for Dry Mechanical Decontamination of Corners, Edges and Impurities for Nuclear Facilities. The project ran out on June of this year, and so we had a next follow-up research project. The 2 main focus points of the project were comparison of the performance parameters of the currently used tools for decontaminating inner edges and corners, and after that part to develop and construct new demonstrator tools to do that better. So the follow-up research project Econt 2 started right after Econt 1 on 1st of July, so we're pretty fresh into it. I told you we were overviewing the currently used tools, so what is state-of-the-art for decontaminating inner edges and corners. So we've got needle guns, milling tools, or concrete grinders, as you know it from like conventional dismantling or deconstruction. And as you already can see, these tools are not really built to decontaminate inner edges. So therefore, we thought about new cutting technologies and developed some. So these are the first schemes or our thoughts. We developed all in all 4 demonstrator tools with different techniques. So from left to right, first we've got a step cutter with co-rotating direction diamond disc all in all. The second one is step cutter with contrary direction of rotation. The third is also a step cutter with contrary direction rotation of the diamond disc, but with a transmission to get the concentric or the middle diamond disc concentric moving to the, or contrary moving to the other diamond disc. And the fourth one is a special one, oscillating tool head. We'll have a closer look on that later. So first, that you can get an easier thought what we did. These are some CAD drawings of our prototypes or prototype tools we tested. That's the first, the second one, and the third one. We will have later more explanation to each demonstrator. So to test all of these tools, we designed a test bench. It's like a steel box with a linear unit in it. The linear unit is attached with carbon joints that allows it to move in every 3 dimensions completely freely. We can tilt it. We can use it for like nearly every test we wanted to do. So on the right picture, you can see the test bench built, and we have a closer look inside of the test bench. That is the linear unit where the tested tool drives forwards and backwards. That is, for example, the first tool we used or we tested. And underneath the linear unit, you can position a concrete block and get the test results live in. And also on the right picture, you can see we built inner edges with 2 concrete blocks and use the demonstrators in it to test how good they perform. So that box looked quite simple, but we've got a lot of hidden technique inside of it. We've got some internal factors, so what are we putting into our test? For example, the feed rate, how fast are the demonstrator going? We measure that with our linear unit, the removal depth with the cardan joints, the direction of rotation itself, that depends on the tool, and also the direction of operation. Are we going with the rotation or against the rotation? And that enables us to get a lot of external parameters or like test results out of it. We measure forces and torques with a hidden 6-axis sensors. After the test, we go over the concrete surface with a laser scanner to measure the surface roughness for clearance measurement afterwards. Also, we have a vibration meter built inside to measure the vibrations that occur to the user or the construction site worker. Also, sound level meter. Of course, we measure the demonstrator weight, the amount of dust with a real-time dust monitor, and the particulate meter, grain size measure, in German Feinstaub, some of you know it. So we started our test series, and we did over 60 tests with average 6 tested parameters, so we've got quite a lot of data. That looks quite that, but I'm not going into detail in those 15 minutes with you. So let's put it all together in a kind of a middle conclusion for each demonstrator with deeper details for the demonstrators, as I promised. So the first demonstrator, step cutter with co-rotating direction of all 5 diamond discs. So that is how the tool looks like. We've got 5 diamond discs in it. Each diamond disc has a different diameter from outside to inside, so you can really get those 90-degree angles to really cut inside of edges of nuclear power plants, for example. We've got one engine to move all of those diamond discs. That will change on the other demonstrators. So the big pluses that the result shows, we got pretty low forces for the user. The amount of dust is also pretty low. The demonstrator weight of that demonstrator was pretty light, and also particle matter and surface roughness was pretty good. Big minus points of the tool were the vibrations and sound levels are pretty high, so we've got a pretty loud machine. The second demonstrator tool we developed is a 6 diamond disc cutter with 2 engines, and each of the engines move the diamond disc in contrary direction to the other side of the machine. So the big pluses were we've got pretty low sound levels, and the vibrations are also pretty low, but as you can imagine, the demonstrator weight of 2 engines is pretty high, and also the amount of dust produced while operating is pretty high too. So then we combined those benefits. In the third demonstrator, we've got 5 diamond discs. The middle disc, as I said, is moving in contrary direction to the outer discs. That's because of a built-in and patented transmission we built. So the whole machine or tool only uses one engine to operate. The big pluses were we've got the amount of dust and particle matter pretty low, but because of the transmission, that is still something to develop. The demonstrator weight is pretty high. The surface roughness is not where we want it to be, and the sound level is pretty high. And our fourth demonstrator, that is something completely different to the other tools we developed. We've got an oscillating tool head that is like a like a vibrator. It got only one engine and brings the tool head to oscillation, and the tool head is like formed for especially inner edges with diamonds on it. Like we are also using diamonds to cut, but with the oscillating technique. So we've got a pretty low demonstrator weight, and because of the geometry of the tool, it's especially usable for inner corners, not just inner edges, where like floor and wall come together, but where two walls and the floor come together. The minus points are the feed rate is lower than from the step cutters, also the removal depth, and of course, because it's an oscillating tool, the vibrations for the user are pretty high. So that brings us to the results from the laser scan. We've not got the oscillating tool beneath them because it's like hard to compare step cutters to oscillating tools. So we've got the first, the second, and the third demonstrator we use. And as you kind of can see, the first and second demonstrator tool deliver pretty good results. The third demonstrator gives us a hard time. We've got some leftover concrete bridges that makes it a little harder to do the clearance measurement afterwards. So that is a laser scan or a 3D display of our inner edge before our decontamination process and after our decontamination process. I think that is with demonstrator tool 1, and it gives pretty good results and looks pretty nice for decontamination. But as some of you may have seen the Oppenheimer movie, theory only will take you so far. So we did some practice tests at the nuclear power plant in Obrigheim with our industry partner Satkern together to get some practice tests or practice results. So we tested all our demonstrator tools in ergonomics, performance, and surface roughness. To go quick over it, the ergonomics of the first step cutter was pretty good, and also the oscillating tool, but demonstrator 2 and 3 were a little bit too heavy for construction workers to use them 8 hours a day. But the big points were they had a good performance, like overall performance to remove the concrete. The oscillating tool is good for inner corners, but the overall performance for inner edges is pretty low. The surface roughness were overall pretty good, except for step cutter number 3 with those leftover concrete bridges. That is a picture of a step cutter of us in use. So I want to come to a conclusion of Econ 1 and an outlook for Econ 2. Big topic or big theme is keep the good things and improve the bad things. The research project we had delivered 4 fully working demonstrator tools. The test bench we designed showed us which demonstrator performs well in which specific field. So we have a closer look on the forces, torque, sound level, vibration, surface roughness, dust, and some more aspects. But what really brought us forward was the practice test on the nuclear power plant or on the construction site or deconstruction site, which showed us again which aspects are really important. For example, the demonstrator weight is a big point. So therefore, we also plan to improve these points in the future. Like, for example, the tool weight, as I said. Then we want to focus on getting our tools a little bit smaller to even make them more handy. Also, the surface quality, it is already good for most of the demonstrated tools, but we want to improve it even more, especially for the clearance measurement afterwards. And we are planning to do an exact depth performance to get like really exactly in beneath millimeter performance level. And as also in the first project, we always keep an eye on the safety improvements for the workers, so we want to have no accidents with our tools on the construction site. And with that, I'm coming to an end, and thank you for your attention.
Thank you, Mr. Rentschler, for this very interesting presentation. We are good in time again, so there would be enough time for one question from the audience. Okay.
Hi, thank you. Tom Makrowski, SciClive Group EDF. I've got a question. What are the possibilities of linking this tool with this robotic tool that your colleague presented first this afternoon?
The possibilities are there, I think. Right now, we focused on problem areas of decontamination. So, like, I think for like a big even wall, there are some machines that you can use, but the problem areas like inner edges and corners, but also like door frames or like statically built under beams on the top of a room. are pretty hard, and those problem areas are usually done by hand by construction worker. But of course, the tool is also pretty useful when you've got a robot system that completely freely operates in a room. Then that would be also a tool you can attach to, for example, the Manitou.
Okay, thank you. Another question? Yes.
Michael Walz from the EVN. Another question would be, the main weight is coming from the batteries, isn't it? Or doesn't it? Or really from the engines?
Right now we're not using, can't go back. Right now we are not using battery till now. We're operating by cable at the moment because when you have those steam sucking vacuum on the tool, you already have those cables. So right now we're using cables. So the weight depends on the prototype, comes mostly, or like, I would say 1/3 from the engine itself and 1/3 of the diamond disc, and then it depends on which demonstrator the rest builds, like the transmission, or if that's two engines, that's more. So, but you mentioned it, we started working with the Bosch B-Turbo Winkelschleifer. It's like a kind of a, or not so new model to work with accus or batteries. So we're already in the process to develop that to like a battery driven system. Or yeah, I'm not mentioned it. Like the first demonstrator, for example, weighs around 7 kilograms. It's like 5 diamond discs and the engine, so it's pretty light for a deconstruction tool, you can say. But like when you're working with 6 diamond discs, big transmission and 2 engines, the machines get pretty heavy to like 10 to 15, even 20 kilos. And that's simply too much for a construction worker to work for an hour or even 8 hours with it.
Thank you, Mr. Rentschler. Then we can come to the next presentation that will be given by Mr. Yeah. Presentation will be given by Mr. A.Ridao. He already introduced himself at the beginning of the session, so we can start directly with the presentation. And the title of the presentation is The Use of Digital Twins for Waste Estimation in Nuclear Facilities, Dismantling and Decommissioning, the PLEIADES project. Mr. A.Ridao, the floor is yours.
Thank you very much. I would like to thank you everyone again for coming to this presentation, as well as the wonderful organization of this symposium, safeND 23, for giving me the opportunity to address you. Nowadays, a considerable number of nuclear power plants worldwide have reached or will reach the end of their life cycle. And they will need to be dismantled within the next few decades. Dismantling and decommissioning of nuclear facilities is a challenging, complex, and hazardous task that was never foreseen at the time that the current nuclear facilities were designed and built. And as a part of these decommissioning and dismantling activities, waste minimization and waste management have an essential interest. So today I'm more than happy to present you this EU-funded project, which is called PLEIADES, platform based on emerging and interoperable applications for enhanced decommissioning processes on behalf of the consortium project. So I will start my presentation with introduction, digital tools, objectives, demonstration on real use cases, the organization of the project, the results that we get until now, and I will do a focus in the use of the digital models, and I will do a summary, and I will explain what are the conclusions and the further steps that we aim to follow. The consortium of the project is composed by 14 partners coming from 7 different countries. They are academics and research organizations, small and medium-sized enterprises, and industrial companies, as well as a technical safety organization, representing different stakeholders and providers of the nuclear dismantling domain. Stakeholders and providers of the nuclear dismantling domain. So I saw one representative of one of the partners of SecLife who put the question previously. So the partners joined forces to demonstrate an innovative digital approach and a new methodology for improving selected key tasks related to dismantling and decommissioning. The project has received funding from the Euratom Research and Training Program 2014-2018, and it will end this year, late November. One of the big challenges when we want to implement digital tools in a nuclear decommissioning project is that the effort needed to digitize a plant, especially an old one in an existing facility, is very high. So one way to help with this burden of time and cost is to reuse data that has been generated by other tools. So far, most of these tools are standalone solutions. So in this project, a series of cutting-edge digital tools are collected and implemented in a platform that is tested on real use cases. These technologies have different purposes, like the production of point clouds with robotic platforms equipped with laser scanners, as my colleague Mr. Kazemi explained previously, virtual reality simulations, tools compatible with international structure for decommissioning costing, decision support tools, or tools for waste routes and activity assessment. With all this, the PLEIADES project sets a series of objectives that are creating a new digital methodology to improve the nuclear decommissioning, define an ontology and procedures for the digitization of nuclear facilities dismantling and decommissioning, and facilitate higher standardization required for international application. And of course, the ultimate goal of the PLEIADES project is to protect workers, protect the environment, and optimize costs. To achieve these goals, the project aims to develop digital twins through a BIM technology-based platform that helps take decisions. BIM means Building Information Modeling. 3 use cases of real facilities undergoing the decommissioning and dismantling process are used in PLEIADES. The first one is the facility of Santa Maria is the Halden Research Reactor in Norway, a nuclear research facility operated by IFE. The second one is Santa Maria de Garoña, operated by Enresa, which is located in Burgos, Spain. Sorry, no, it's not operated by Enresa, sorry. Enresa is in charge of the D&D task. So this nuclear power plant was shut down in 2012 after 41 years of operation and has been in the D&D process since 2017. And the third one is the nuclear maintenance facility Base Chaude Opérationnelle du Tricastin in the south of France, operated by EDF, Électricité de France. So the available data is collected regarding 4 requirements, which are cost and planning, radiation exposure estimation, scenario studies, and waste assessment. This data is incorporated in the platform, following a BIM methodology in order to develop the digital models that are used to perform the simulation and compare the obtained results with the referential results. The PLEIADES project is structured in 7 work packages. The first work package is the requirement analysis, specification, and test design. The work package 2 is the PLEIADES platform development, which is the more technical part where the architecture of the platform is defined. The work package 3 is the implementation of the PLEIADES platform on real use cases, and here the user stories that were defined in the work package 1 are performed. I will explain what these user stories are in the next slide. The work package 4 is the modeling and results evaluation. Work package 5, standardization efforts, exploitation and training. Work package 6, dissemination, communication, and stakeholders engagement. And the work package 7 is the project coordination and management. So in the work package 1, the commissioning oriented ontology was defined. This nuclear ontology, based on a specific decommissioning terminology, provides a common understanding of the PLEIADES process. In order to demonstrate the PLEIADES concept, 6 user stories have been defined based on the 3 real-life use cases. Three of these user stories, the three first one, are based in 1 case studies each one, and focus on characterization of the contamination of building surfaces, radiological characterization, alternative scenarios to basic decommissioning activities, and the other three focus on risk management, uncertainties, regulatory aspects, and waste management strategies. In the work package 2, the architecture of the PLEIADES platform was defined. The PLEIADES server is a central server that contains a back-end with database and file storage, and a front end with the identity and access management solution, as well as a gateway. The identity and access management solution connects with PLEIADES generic software, and the file storage and database connect with a gateway, and this gateway is accessible by the PLEIADES partners with the connectors and the API. So after being specified, the result is that this platform is developed and tested and is fully operational. In this slide, you can see some example of simulations in each of the 3 use cases. The first one in the Halden research reactor, we collected data and we performed a task corresponding to the user story 1. Sorry. So in this work package 3, the 3 main tasks are performed in order to develop digital models. So the checking and validation of input data completeness, led by SciClive. Here, the physical and radiological inventory, among other features, were collected. The other task is the development of 3D models, which was led by KIT. And here, our institution performed activities to analyze the input, identify gaps and problems, and propose and perform activities to complete the models. The data feeding the digital models is crucial and requires data collection and integration, data security and assurance, and data completeness verification. The output of these activities was used by IFE in the task 3.3 called Development of the BIM Models. The whole process is iterative until the model contains all the necessary information required to perform the user stories simulation. Among others, each simulation using a digital twin considers a physical and radiological environment and estimate the waste produced, the waste management process, and the waste management cost. So here you can see some examples of the simulation. In the Halden Research Reactor, IFE use the tool VRDOSE with RadBeam, BeamSync, and RISC-Beam. A comparison of manual and remote radiological characterization plans for selected components was done in the Halden Research Reactor Hall. In the case of Santa Maria de Garoña, when you see it in the middle, in Spain, the simulation of the evacuation of a heater was carried out. The software DEM Plus for nuclear, developed by SecLife, was used, and the user story consisted on a 3D supported versus digitally enhanced dismantling. In the case of the BCOT, Base Shot Opérationnel du Tricastin, also the software DEM Plus was used, and the test consisted on the manual versus automatic decontamination of builder surfaces. As a result, the commissioning planning activities were demonstrated with focus in cost estimation, waste estimation, dismantling, visualization, risk management, and TSO regulatory reviews. So as a summary, a core nuclear decommissioning ontology was developed in this project. PLEIADES is an open, robust, and flexible platform. It is open because the API interface is publicly available. It is robust because a large amount of data can be processed, like 3D models, point clouds, this in a structured database. It's flexible because any software, independent from the technology, can connect and benefit from the common data environment. And the 6 user stories were successfully demonstrated, utilizing various technologies like 3D modeling, virtual reality, mixed reality, computational analysis used at different stages of the commissioning planning. So our conclusions are that we need to continue in the development of the ontology and the API. We aim to extend the coverage of the decommissioning planning activities that can be supported by the PLEIADES platform, meaning not only nuclear, but also in conventional decommissioning. And we aim to use other digitization technologies like artificial intelligence, robotic, or integration with sensor networks. So I am arriving to the end of my presentation. These are the sources, and thank you very much for your attention. If you want to get more information, here are the links of the projects, and if you have questions, I will be glad to answer you. Thank you very much.
Thank you, Mr. A.Ridao, for this interesting presentation. I think we've got enough time for maybe one question from the audience. Yes.
I can use this one, no? Okay. Yeah. So thank you very much. It's a fascinating project. My question is, how is it perceived from the waste management organization? So is this tool already used? Are they going to use it? Because it's a development, a European project. Mm-hmm. So how is the, let's say, the stakeholder perspective?
As I explained in this slide, each one of the partner has already developed a tool. We have a partner from Belgium, Tractabel, which belongs to the group NG, and they have a tool that is called Livestream that can estimate the waste routes and activity assessment. So we have been working on that, but the results have not been disclosed yet. So here we have the different user stories, and it is in the user story 6, if I am not wrong. So the results will be disclosed soon.
Okay, so the waste management organizations are interested in this tool. Okay.
Yes.
This is very important.
Thank you.
Bertrand from Andra. I have a question dedicated to the standardization. You just show us that there is a task dedicated to this aspect. Could you tell us more about what is inside this standardization? It's about the data or whatever?
You mean in the work package 5, we are working in the standardization efforts, exploitation and training. Well, this is an European project, and as we have been working in 3 different facilities, these facilities are in a different country, and they follow different rules, and the bureaucratic all the bureaucracy is different. So at the end of the project, we want to create a common methodology and a common understanding at the European level and then at the international level. So now we are working in this work package, and we also invite interested people to join the project and to help us to develop this.
Okay, thank you, Mr. A.Ridao.
Thank you.
So now we will come to the last presentation for this session. That will be given by Mr. Chaudry, also from the Karlsruhe Institute for Technology. And the title of the presentation is Wet Sieving and Magnetic Separation for the Treatment of Radioactive Secondary Waste Produced from Water Jet Abrasive Suspension Cutting. Mr. Chaudry.
Thank you. Hello and welcome to my presentation on the topic of wet sieving and magnetic separation for the treatment of radioactive secondary waste produced from water jet abrasive suspension cutting. My name is M.J.Chaudry and I work as a research associate at Institute of Technology and Management in Construction. We are working together with Institute for Nuclear Waste Disposal, and this project is funded by Federal Ministry of Education and Research. Firstly, I would like to introduce a water jet abrasive suspension cutting technique. This technique is usually used in nuclear sector for the dismantling of reactor pressure vessels and its internals. This technology uses a pure water jet that passes through a thin, a specially shaped net nozzle, and with high pressure and velocity around 2000 bar, and that cuts through the radioactive, that part of the material. So this process, this technique has numerous technical advantages. For example, that it can be remotely controlled, that provides maximum safety for the operating personnel. And this technology can be used under water, so that provides no aerosol byproducts. Moreover, the cutting capability of this technology is wide because it can goes through different shape. It can cut through different shape of the material. By having these technical advantages, it has a downside that it produces a large amount of secondary waste, which I will explain. So this technology creates a large amount of secondary waste. For example, if it's used in a nuclear technology, so it uses water and abrasive particles mixed together on the internals. And the steel particles that produced are radioactive, and which produces in terms quite large amount of secondary waste when mixed with the abrasive particles. So we have done electron microscopy from this material gathered, and by backscattering light, we have seen that from the sample, it contains only 2% by mass of activated steel particles. The rest is just abrasive particles, which can be reused, that can lower the amount of secondary waste. So this idea struck, and then so that was the context that this technology can be used enormously. But the amount of secondary waste produced, that has hampered the use of this technology in nuclear field. So we devised a principle which uses different types of unit operations, for example, sieving and magnetic filtration, to lower this amount of secondary waste, and by creating a new sideways to reuse the abrasive for the next new cut. So in this technique, we uses firstly sieve, which separates which separates the used abrasive and steel particles. So from the sieve, the fine fraction which contains abrasive particles and fragments from the steel particles, they are removed and disposed. While the upper fraction, which is coarse fraction, that contains the large steel particles, is then sent to magnetic filter, where it removes these large steel particles, and the abrasive can be reused. So that was the principle. Then we have also devised and developed a small-scale pilot plant on this principle. So here you can see that. Here we worked on with non-radioactive material for our first project. So here the suspension is created by which have small steel particles and abrasive particles, and then this is pumped into the sieving for sieving. And after the cycle, the coarse fraction is separated in a bag filter, and in the next cycle, which the coarse fractions that also contains large steel particles were sent to this developed and devised magnetic filter, where it separated the bigger steel particles. And from this small scale pilot plant, we normally used around 500 grams to 600 grams of sample material to test our plant. And in the end, there were a reduction from 50 to 75% of the material was reusable for the next cut, and it was 99.9% pure. So, but there were a lot of complications in this batch operation. For example, as the abrasive particles are really sharp, so they caused clogging and deterioration of the switching valves that we used for the different operations. And due to this difficulty, because we have to switch the two processes. For example, for the sieving process, then there is an operation of cleaning the whole system, and then comes the magnetic separation. So these interruptions created a long time for a small amount of sample to be worked with, and that causes a lot of problems with the valves, switching of the valves, and the separation rate was really low. The bigger concern was that there was a rapid overloading of the magnetic filter with the particles, and the solution to this problem lies that we should move to the continuous operation. And the benefits of the continuous operation, that we have to develop a new principle, and we have to develop a new continuous sieving process and continuously operated magnetic filter. In this regard, here I would like to show that how the magnetic, these rods, they are rapidly overloaded with the magnetic particles, and after some times, the results were not really the same. That's why we have to find a new way or new method for this magnetic filter. And there were impurities and residual material always lies in the in different parts of the magnetic filter. So in this new project, we devised a continuous operation that uses three different types of three pumps and one continuously operated sieve and continuously operated magnetic filter. Here is the process flow diagram that I would like to just go through it. That in this agitator, the suspension is being created, and then it is sent to the sieve. And from there, the coarse fraction is sent by pump to the magnetic filter, while the fine fraction is sent back to the fine particle filter. It seems quite easy in this process to see, but in reality, when we wanted to test it, it's quite complicated, which I would like to show in further next slides, that how this continuous sieve and this continuously operated magnetic filter works. So for the continuously operated sieve, as we said that we would like to perform the experiments with radioactive substance, so we used a vacuum system so that it can be pumped on the top of the sieve here. So if any kind of clogging that occurs, so it will, if the vacuum is not created, so the process will already stopped. So from here, the inflow comes of the inflow of the suspension comes on the top of the sieve surface, and as the sieve is equipped with vibrator and it is halfly under water, so the particles move towards this point, and the fine particles, they just move in the water. So here the coarse fraction is just taken out by the coarse fraction pump, and the fine fraction can be pumped by the other pump. So here, we have tested this continuous sieve, and the what we call it sieve error, that is really low, and it lies between 3 to 4% now. So that shows that the particles what we really want to separate, these are like only 4% of error is shown by this continuously operated sieve. So for example, for only one time the particles move through this, and there is only a 4% of error. And it's quite remarkable for this developed sieve. Similarly, we developed this continuously operated magnetic filter quite recently, and it is still in process, and we are doing some preliminary tests to check it, but it still has shown quite good results, and it is also patented right now. It's a newly developed closed continuous magnetic filter system. Here, here on the right you can see the technical implementation, and on the left how the principle works. So firstly, I would like to show the principle. From the top, here comes the inflow. For example, the suspension containing steel particles and abrasive particles. So this device, we call it R divider here. And this pipe, this shows the pipe section, and this is the separation pipe. There we have rotating magnetic rods here. And here you can see that these magnetic rods are in contact with motor, and they just rotate. So when the abrasive particle mixed with steel particle comes and they are in contact with this rotating magnetic filter, they just separates the steel particles, and they went to this side, giving us the abrasive particles here in the outflow. And this can be done in a continuous process, and it's just rotate and just separates the whole flow. Here we have also did some preliminary tests, and here it just the photo of this magnetic filter, and you can see from this pipe at the top comes the suspension, and these magnetic rods just rotate, and there they separates this magnetic particles this side, and the abrasive goes down. Here you can see the video as well. There you can see the magnetic particles, they're just going down, and it's just separated. Here as well, some of the particles. So this was just a preliminary experiment we performed, and it's still in the phase for further testing. So the preliminary results that the first experiment we performed that only steel particles, 5 grams of steel particles we took and just ran it for 20 minutes, and it was like a batch operation. So we checked, and from the theoretical extrapolation, we have seen the result that for every cycle, it just rotates from 0.5 to 1% of the steel particles in just one rotation. And as I told you that it's just the first step in this continuous magnetic filter, and we are still hopeful that we will perform much better with the results in this. So the outlook is that in this project, we want to perform a combined test at the same time with the continuous sieve and continuous magnetic filter with abrasive steel mixture from which comes from the was cut. So and further we, as I told you, that continuous sieve we have quite really good results, and but with this magnetic filter we really want some improvements in terms of geometry of the piping. For example, we can look for the material used for this R divider, maybe the thinning of the walls, and also by creating some kind of lump, so the contact between the magnetic rods and the suspension would be much better. Similarly, right now we are using membrane pumps, and it causes some kind of pulsation that sometime will loses some material, and maybe use of the this peristaltic pumps, and as shown in the figure, we also want to use more R dividers in parallel and see how the results are. Thank you for your attention. If you have any results, let me know.
Thank you, Mr. Chaudry, and for this very interesting presentation. Are there any questions from the audience? No, everyone is tired. Okay, then I would say when there are no questions, again, thank you, Mr. Chaudry.
Welcome.
And then the session for today is finished. Thank you very much for the very good presentations we heard and for the questions we got here from the audience. And let me remember you that tomorrow there will be another session dealing with decommissioning. So if you are interested, please join this session. And I think the day will close with some closing remarks from Mr. Hamann. So I give the word to Mr. Hamann.
Thank you very much for your input, both of you. Yes, welcome again. I can say now, after almost 9 hours after I was able to speak to you and welcome you here at Café Moscow. Not as many people here, but I assume that resilience was also defined in terms of a lot of input, a lot of new ideas, a lot of exchanges, good talks, hopefully you already enjoyed, and you'll now have to take with you and consider and reflect upon them. Thank you for coming back, and for this final closing remarks, I would like to call on stage 2 guests. One is Fanny Böse. I've already seen her. She's a PhD student going for a Doktorarbeit at the base. And the other one is Carsten Reiter from the Technical University in Darmstadt. He's a structural geologist. I hope this English translation is the right one for Strukturgeologe. Have I seen him already, or have I met him already? I'm not sure. Oh, he's still busy. Then I'll be happy to have one guest, if I may say so, because I don't want to keep you here any longer. Thank you for coming. This is Fanny Böse, my distinguished, and Mr. Reiter as well. Welcome as well. Thank you for coming. Maybe you can come into the light a bit more. What we're going to do now is have a little look upon this very first day here at safeND. How was it for you? And if you would also already like to answer my next question, that is, what does resilience now mean to you after these first 9 hours here at the symposium? We have a microphone here.
I have a lot of notes.
Okay, you will present your notes to us. We'll be delighted to hear them.
It's just, especially this side. It was dense for me. Do you know the feeling of mental overload? Like you have a lot of input, you have a lot of insights, and at the end of the day, you know nothing anymore. So this is kind of my state of mind right now. So there's a book, a lot of notes, a lot of insights, especially the keynote from Alison McFarlane was super insightful for me with the nuclear waste streams. So she was closing some knowledge gaps for me. And then I heard a lot about resilience and a lot of perspectives and definitions. It was thinking the unthinkable, or our current site selection process is not resilient enough because it takes too long. So there are a lot of different perspectives, and I tried to find my own definition from resilience today, and it is a multidimensional system process that moves towards time and to an uncertain future, but it should be navigated by a system traits of safety, democracy, iteration, transparency, participation, and it should hurry up.
Thank you very much. Wow, interesting. A lot of input, for sure. Carsten Reiter, please, what was your experience today?
Thank you very much. My experience for today is also that it's a quite extensive day. I've seen many interesting talks. What is also, for me, really nice that I met so many people. So there was many people which I know already before, but I was also met many new people. And I think that's, for me, was more or less the most important thing, to meet all these people and having discussions on completely different subjects. That means it's really technical stuff. It means from the certain perspective, but it's also just a broader view, what in the direction you're asking for. So what is the general direction of the further development in Germany, how it will work, and in which way we will find this repository. And for me, I'm not involved in detail on these more general aspects. So I'm more specific on certain aspects, but I would say what is really important, what you already mentioned, so that it's really important that the process is open, that it really learns, and that as much as possible the people in the public, so that they can follow what is going up there, and not at the end then they say, okay, something came along, so and they didn't know before what happened, and that could be one problem in the future, and that would be necessary to make it safe that all the people have the chance to participate in this process.
Thank you. What can we do better? Tomorrow is already very close. If we'll have a chance, we'll do it. But is that working for you, this constant flow? You can change from one panel to the next session and, well, kind of browsing around and pick up some information here, use the opportunity to talk people over there. Is that working for you?
Yeah, I think so. And I think it's maybe for such a conference, it have to be dense. Otherwise, it doesn't make sense. So it's that maybe such a conference otherwise would take not only 3 days, or it would take maybe 2 weeks. So, and then maybe I wouldn't say that would be a good chance or a good way to do this. It have to be dense anyway, I would say.
Thanks. Any input from you?
I think it would be more enjoyable for me if I wouldn't do networking, absorbing insights, and still doing my last preparations for my oral presentation on Friday and the workshop. You're all invited to come. So I think it works, but for me it's kind of stressful.
Good. Now it's the time to relax a bit, enjoy the rest of the evening, come back tomorrow morning. All of you, hopefully, will start again right in the morning, and tomorrow evening we'll have a dinner. It's still on the agenda, and we're looking forward to it very much. We've even been consulting the weather gods, and they are fine at the moment. We'll see. So Come back tomorrow. Thank you very much for coming today. Enjoy the evening, whatever you're going to do in this very big city, but just be back tomorrow. Thank you very much. Bye-bye.